Now, the topic that we covered earlier, we have a number of modules to implement these signals and systems experiments. And these modules are actually come with software, and we have a control panel which controls the coefficient gains of those modules. So the students can set up, and let me just quickly show you. Here are the experiments we have that we mentioned previously for our signals and systems. There's Lab 1's Introduction to the Signal Systems modules. Number 2 is Special Signals, the Characteristics, Linearity and Non-Linearity. Chapter 4 is a lab on convolution. Then Integration, Correlation and Matched Filters. Exploring Complex Numbers and Exponentials. Fourier Series Analyzer. Again, the topic that you mentioned earlier. Spectrum analysis of signals. Now, continuous time structures, poles and zeros, where the students are actually build the Laplace structures, sampling and aliasing, A to D conversion. Now, again, the ones you mentioned, discrete time, FIR filters, and IIR. So what that means is...
Can you please go back a little bit? Sorry, a very short question. So I can see that you have, yes, a Fourier series analyzer. What we do, we're giving to the students periodic and aperiodic signal, and first they have to do Fourier series, the first thing for periodic signals, and we're doing, they do some simulation, and after that they do in Fourier transform, because Fourier transform can use for aperiodic signal also, and they're doing a chirp signal, for example, and they do some experiment. I guess you can have different signals to generate, yes? So you have periodic and aperiodic signals to be able to generate, yes?
Precisely. We provide in the module, in the control module, we provide an arbitrary signal generator. So we provide a few signals and a template, but you can program in the signals and load in the signals that you want. So you've got complete control over the types of signals you want the students to analyze.
Yeah. So box function. Yeah. Okay. Thank you very much. So you have here. Just can you stay just 1 second, please, back for the signal module, because that is another course I'm teaching, and we have 2 courses in signal processing. So, signal and characteristics, linear, nonlinear, convolution. Yes, you can do convolution in discrete time and continuous time. So we teach them continuous and discrete time. So we have a continuous time system. We have discrete time system. Just I'm telling you what we are in the curriculum. Complex number exponential, Fourier series analyzer, good spectrum analyzer, and signals, poles and zeros in Laplace domain. So we're doing mainly in Z plane.
That's the S plane. The Laplace.
Getting starting analog to digital conversion, sampling, aliasing. Yes. Okay. Thank you very much. Thank you.
Okay.
Thank you.
So this software, I'll show you. I'll answer. I think you probably have some questions, so I'll answer some of these queries. So here is obviously the block diagram of a discrete time system. So what we're doing is each of these coefficients is what the software controls. All the rest is hardware. So it's from the computer screen that the student types in a value for that coefficient, and that gets transferred via USB into the module, and that's what it sets there. So the student actually builds that structure block by block. And this software, you see here, adjustable gains for each coefficient setting. That's what is shown. That's what happens up here. So we have actually one tab for each of those experiments you saw. So each of these experiments has its own tab. So whatever instrumentation, whatever different data or whatever parameters need to be measured or adjusted, or displayed. There's one tab there for each of those experiments, including, you see here, FIR filter. So here you see the Z plane, here, the unit circle. And if you can see, there are poles and zeros plotted. So when a student types in the coefficients, the poles and zeros that result from that are actually plotted in that unit circle. So if the student plots in coefficients where the poles go over the unit circle, the poles will be plotted outside the unit circle, and the student will obviously have an oscillator rather than a filter. And the student will see that in real time. So if they move the poles too close to the unit circle and the system is, there's a bit error in the system, they'll see it breaking into oscillation and settling and so on.
So yeah, we're looking for the stable or unstable systems. Yeah, that's very good, because the students, we give them a lot of calculation and they can see it on the, they can check it and they can see on the, using this experiment.
Yeah, they get visual, they get instantaneous feedback. And the other thing is we actually map our chapters, our labs, against a number of, actually here only 4, but we actually map against 8 different signals and systems textbooks. The most popular we hear of is Lathy, but then there's Oppenheimer and Zimmer and some others. So we actually provide
yeah, we're using, okay, can you Oppenheimer? Yeah, McClellan, yeah, McClellan up there also, we're using that one. We are McClellan up there, yeah, this one, McClellan DSP first. And yeah, we're using Oppenheimer signal system 1.4. Yeah, thank you.
Okay.
Yeah, thank you.
So there we're mapping. So that answers an early question that you had regarding signal systems. I'll now just very quickly go through.
Yeah, thank you.
You know, for example, MSK, OQPSK, Pion 4D, QPSK, where again the students actually see the real, signals in real time. These constant amplitude schemes. Ultra wideband. Again, we implement ultra wideband, but at 100 kilohertz. However, the pulses are exactly correct. So we are actually scaling. That's why TIMS is a modeling system. We are scaling these ultra wideband schemes down so the students can actually see the pulses instead of at the real commercial or industrial bandwidths. The OFDM we have covered. So, and the other one that we have covered is the teaching concept. So this document of 4G and 5G experiments sort of ties together where TIMS sits with the latest experiments. And what I have to point out is that when RMIT Melbourne first purchased TIMS, probably none of these experiments in the 4G and 5G document existed. And some of the modules.
Yeah, yes, of course. But, that is this latest one, yeah.
But all of these experiments can be implemented on RMIT Melbourne's TIMS systems. Because when we release new modules, they're all forward and backward compatible with the TIMS units that were purchased 10 or 20 years ago. So that's an important thing to remember. So even the first universities who purchased TIMS many, many years ago, University of Technology, Sydney here, and the Royal Military College in Canberra, they can all implement on their old TIMS systems the very latest experiments that we have released, because the TIMS units have not changed. We can maintain that compatibility. So that covers an overview of TIMS capabilities. Now, just in the time remaining, let me show you one example of a spread spectrum experiment, just to show you that for most people, spread spectrum is this quite complex, difficult scheme. But if we break spread spectrum down to its core concepts I can demonstrate direct sequence spread spectrum very quickly and easily. So let me pull this experiment apart that we had. I'll just move these modules. So